Today, we will finally prove the torsion formula, which says the torsion tau is equal to the determinant of x dot, y dot, and c dot. And those are just the first derivative from the x, y, and c right here. And the r is the position. And then next, we have the 2 dots, which is just the second derivative. And 3 dots is just for the third derivative. Once we have the determinant, we will divide that by the magnitude of the cross product of the velocity and the acceleration, and then square that. Yes, this right here is definitely not an easy formula. And we can also write this as the following. We will find the determinant of the velocity, which is just the first derivative from here. And then the acceleration, that's just a second derivative. And we can also write the third derivative as the factor j for the jerk. Okay? And then divided by the velocity cross the acceleration square. Yep, first and also the second derivative. So definitely it's not easy, and we have to use a lot of things that we did from the curvature video and also the Serif formulas. So let's take a look at those things right here first. First, let's review from the curvature video. The velocity is equal to the magnitude of the velocity times the unit tangent factor. And remember, for the velocity, this right here is the derivative of the position with respect to t, but the magnitude of the velocity, which tells you the speed, this is the derivative of the r length s with respect to t. They are quite different. This right here, you can think about it as like a quantity, but this right here is still a factor. And then from here, we differentiate it again. That's how we end up with the acceleration, and then we end up with this equation. And notice the derivative of the speed, you can write it as d2 as dt2. Well, just keep it like this. But this is not the same as the acceleration, so that's why I keep it like this. And keep in mind this equation, because just like what we saw earlier, in order to get the torsion, in fact, we have to get the third derivative. So later, I'm going to start with this equation, differentiate it again, and then work with it. All right, and then we also have the velocity cross the acceleration being equal to the curvature times the speed to the third power times the unit binomial factor. And then if we take the magnitude of this, because this is a unit factor, so it's just going to give us 1, right, for the magnitude. Now, check this out. I'm going to combine 3 and 4 together. That's how we are going to get the 5 and 6, 7, 8. Look at this, I will divide this to the other side. So the unit binomial factor is equal to the velocity cross the acceleration over the curvature kappa times the speed to the third power. But this right here, from number 4, we saw that is equal to the magnitude of that thing, right? So it's just velocity cross A over the magnitude of the velocity cross the acceleration. And this is one of the things that we'll be using later on too. All right, then in a separate video, we also did the Serif formula. And notice that these right here, we took the derivative with respect to little t, right, the time. And then we end up with this. So make sure you review all this first before you continue this video, all right? Now, let's go ahead and get into work. Here we go. First, we are going to start with the acceleration. Then we take the derivative with respect to little t, so we can get the jerk. I will write this down for the notation. To take the derivative of this, we will have to use the product rule because they are both functions of little t. So I will keep the first one. And then we multiply by the derivative of the second. So that's dt. And this is where we are going to use the Serif relay later on. And then we add the second one. And then we multiply by the derivative of the first. This is the first derivative already. When we differentiate this again, we get the second derivative. So d2, dt2 of the speed. And you don't have to worry about this right here too much, because later on, we will do j dot b, the unit binomial factor. And then you see this right here, t dot b will be 0 because they are perpendicular. So this right here will be 0 after we do the dot product with b. So let's just focus on taking the derivative now. Then we will have to do this part, right? And okay, the kappa is technically a function of t as well, but you don't have to worry too much. I'm just going to treat this as the first function, and then this right here as the second. So I'm going to keep the first part. So we have the kappa times the speed squared, and then multiply by the derivative of the second. So that's dn dt. And yes, we will use the significant rate for this right here. And then we add the second one times the derivative of the first. I will just write it as d dt of this right here. Later on, we will do n dot b, and again they are orthogonal because the t and b, right? So this part will be 0, don't worry too much. Then to continue, we'll just use the Finesse-Leverage formulas for this and that. So we will get j equals, this right here stays, and this right here, we change that to the speed times the curvature kappa times the unit normal factor. And you can look back to the previous board for that. And then this right here, I'll just keep it. So plus t times the second derivative of the speed. And then continue. Plus kappa times the speed squared. And for this right here, look back to the previous board, you get negative speed times the curvature kappa times the unit tangent factor plus the speed times the torsion tau, and this is how we squeeze out the torsion tau, and then we multiply by the unit binormal factor. And then this part, we'll just keep it, so plus n and then the derivative of kappa times the speed squared. Okay, then you see that this is the only part that has the torsion, and we have the unit binormal factor. So this is why we are going to do the dot product of this, everything by b, because t and b factors, t and n, they are both orthogonal to the factor b. And when we do the dot product, you see this, and that, they will all be gone. So here we go. I'm just going to have j, and we do the dot product with b. And since the order of the dot product doesn't matter, so you don't have to worry too much. Right here, I'm just going to put it right here. So we do this dot b, and then we do this dot b. And then this term, we do it dot b, right? I can distribute the dot product inside, so I can put the dot product right here, and then right here. And then finally, I'll just put the dot product of b right here. Now, you see that n dot b, that will be equal to 0. T dot b, that will also be equal to 0. And here, t dot b, this is going to be 0. But b dot b, remember when you have a factor by itself, you get the magnitude of the factor squared. This right here is a unit factor, so we just get 1. So that's nice. And then n dot b, this is also going to be 0. So, ladies and gentlemen, we get j dot b equals, we have this, we have to multiply it into here, right? So we have the curvature kappa times the speed squared, but there's one more right here, so we will have that to the third power. And then we have the torsion tau, and this is just 1. So this is what we have. And of course, we can just divide this to the other side, and we will get the torsion tau equals j dot b divided by kappa times the speed to the third power. Now, what is b? Well, we know from the t and b factors, b is the same as t cross n, but don't do it like that, because we have something better from the previous board. We can write this as v cross a divided by the magnitude of v cross a. So this right here equals j dot, here we write it as v cross a divided by its magnitude. And then over here we have kappa times the speed to the third power. And in fact, from the previous board, I showed you that this right here is the same as the magnitude of V cross A. So as you can see, here we have one, here we have another one, right? And in fact, the order of the dot product doesn't matter, so I'm going to write this down first. So we have V cross A. Then we are going to do it, the dot product with J. This way we have a very nice order. First, second, and also the third derivative. But this is the cross product, and then here we have a dot product. And then after that, we divide it by this and that, so it's the magnitude of V cross A squared. Now, the final step is, when we do the cross product first, the result is still a factor, and after that, we do a dot product with another factor. The final thing is going to be a scalar, right? Which is just a quantity. It's no longer a factor anymore. How can we simplify this or rewrite it? The answer is this is called a box product, and we can use the determinant of a 3x3 matrix. So ladies and gentlemen, I'm going to write this as tau equals, I'm going to put down the determinant, and we set up V, and then A, and then J. So this means we have a 3x3 matrix with x dot, y dot, z dot, and then x with 2 dots, y with 2 dots, and z with 2 dots, and then the last row is the one with 3 dots. That's what I showed you guys earlier. And then divided by this thing. Oh my goodness. Ah, feels so satisfied. Here is the formula for the torsion. The book didn't prove it, so I wanted to prove it for you guys. That's it.